Okay, so yes. So I posted this bonus homework as requested. It's related to some of the previous homeworks, like the last homework we did, and also somewhat related to the DNS and the email homeworks from early in the semester. Basically, we want to try to figure out what's in a packet trace. You could make it so that it works live too, but for grading purposes and just for testing things, it's much better to work with a recorded packet trace. A TCP dump can be used to, just with a -w. It'll save everything it recorded into a file, and then we will use that as input into our homework. If you want, you could also support without the -i and just open a local interface. I guess it doesn't say which interface to use on it. You can figure something out if you want to sort of have a live service, which would be cooler, right? It's a little bit like TCP dump, except it's more like a little higher level. Like, show me all the pictures that are showing up on this link, or try to capture all the passwords that are on the network, that are like being sent in plain text on the network. Sort of thing. Yeah.
Is last Friday's lecture posted?
I think so, but I'm not sure. Probably no. It's probably not. Right. Yeah, I will do that. Yeah.
Does it require? Are you allowed to use any compiled language?
Yeah, that's fine. Although I would recommend using C. I mean, so I want the language to produce a binary, right? So a compiled language, like you say. I think that you'll have the somewhat easier time if you do it in C, but if you prefer to do it in another language, that's fine. Yeah.
This will like add to our homework rather, because you say like successfully.
Yeah. So say you did 5 of the 6 homeworks, you got 100% on those 5 and nothing on 1. Now if you do this one, this counts as the 6th homework if you want. We just add it all up so you can have like
max 50%.
You can get 600, at most 600 points, right? There's 100% on each homework, so you can get like 600 total. We'll just add them up. But it's not going to count toward your exam score. Okay. Yeah, should be a useful homework in the sense that you get more of a grasp on like all the layers that are in the packet headers and how it all fits together. And you get some refresher on the various application protocols and so on. So I think it'll be helpful in any case, and probably a good thing for interviews as well. Like, oh yeah, I built this packet sniffer. It's I guess a kind of a packet sniffer, application level packet sniffer. Okay, so today, by popular request, we'll talk about some security topics, right? Network security. We'll start with more of on the privacy side, and then we'll talk about denial of service a little bit later. So, privacy and security. I guess the two are closely related. Privacy is something usually that users want, and security is something usually that, say, websites want, but it can go both ways, I suppose. So one common privacy situation might be you are visiting a website and you don't want anyone to know that you're visiting this website for whatever reason. It might be never mind. For whatever reason, you don't want anyone to know what you're visiting. So one option is this thing here. If you hit like that, in Chrome it's Command-Shift-N. It makes a incognito window. So the incognito window, all it does is on the client side try to prevent recording anything on the client side. So you wouldn't, say, have a log of websites you have visited on your machine. And then it'll also try to prevent other websites from identifying you. So as we know, the cookie is something that a website can ask a web browser to return later on when you visit again. A cookie is just some random string, whatever, identifying thing. Website will tell the browser, remember this, and next time you see me, give me this unique identifier again. It's really good for persistent login, let's say. I go to Amazon, I want to buy something, I don't have to log in because they know I'm always on Amazon buying things, right? Every time I open. But if I go to Amazon now, they don't know who I am. I have to sign in every time, and that's because the browser won't send the cookie along. It's not very good from a privacy preserving point of view, depending on what your goals are. Right? So in this case, my goal is just that I don't want any customization from Amazon in terms of what ads I get. Maybe I want to see like the honest price, not the price they give me because I know that I like this product and they're going to jack up the price. You know, there's at least rumors that airlines do this. They see you come back, visit multiple times, and they increase the price. I'm not sure that that's true, but in any case, you can test it. Right? Same thing if you search for your favorite search term in Google, you might get a personalized listing, but if you're interested in what sort of the global view is, then you would use an incognito window, then they don't know who you are, and then you would get sort of an unbiased search result. That can be quite useful. Try Googling for your name sometime, and probably you show up first, but in incognito, maybe not, depending on how common your name is. So in terms of privacy, this isn't a great solution. I'll call this incognito mode. So the problem with incognito mode is it attempts to anonymize at the application layer. And then it doesn't record any trace of a visit. There's some ways that it's unsuccessful in anonymizing, right? There's been some research work showing that you can de-anonymize a browser if you really want to, right? Amazon and Google, they don't care. But if a website really wants to see whether it's you again, you know, they can look at some other sort of unique aspects of the browser, like what fonts are installed on your machine, and what's the resolution of your screen, and how do you move your mouse, and how do you type on the keyboard with what kind of frequency, and things like that can kind of be used to de-anonymize you. Okay, it's not. Seems like kind of spy tricks, but we're at that level here, right? It's NSA sort of things that we're trying to avoid, perhaps. So it might be good to keep that in mind. Also, whatever's in your cache, I don't know that incognito mode, like in Chrome, whether they use the web cache, but probably do. Otherwise, things get really slow. So now you can tell as a web page can tell based on how long it takes to load an image whether you've been on the website before. So then maybe you can give everyone a unique image to see if they've downloaded this image before, then we know that it's the same person again. There's maybe some tricks you can pull like that. But that's all at the application level. There's much more severe problems at the network level, because now it's still your machine. So your internet service provider will see that you're sending traffic to this IP address. And in fact, the website on the other side, they will see, oh, here's this IP address again, like making another request, just like they did a few seconds ago, but it looks like they're in incognito mode now, right? So if you look at the IP address, you can probably get quite a pretty good hint that this is the same machine because it's the same IP address. Now, this isn't always true. If you're behind a NAT, it might be difficult to tell one machine from another. You get some sort of anonymization by the fact that there's multiple people sharing your IP address. It's called mixing. Basically, there's an anonymity set, like how many people could this be? If the number of potential users of IP address so-and-so is only one, then it doesn't matter how much you try to hide yourself. As long as you're using that IP address, then it's you. But if there could be 10,000 different users using this IP address, then maybe it doesn't take so much hiding, and maybe incognito mode will be pretty okay, as long as you're careful about sort of correlations between anonymous visits and identity revealing visits. You don't want to be searching on the same keyword, that sort of thing. Okay, so it's kind of it's a thin shim layer. It's not really nice anonymity preserving. So the next step up, and I think this is probably most common for things like streaming video services, or perhaps like BitTorrent downloads. And so this would be a VPN, anonymizing VPN services. So a VPN is a virtual private network. Basically, it's a tunnel, right? So you send all your traffic to this VPN provider over an encrypted link, and all you do, well, basically everything goes to them, and then on from there to whatever they were meant to go. So you put together an IP packet, put it in another IP packet, send it off to this anonymizing VPN provider, and at their endpoint they just send the packet out. Maybe they change the source IP address. That would make sense. Otherwise it would just be revealing your IP address again. So this is a tunnel to hide the origin of traffic. So the point of this, if you're using a streaming web service, the point of this is often there's region limitations. Like if I want to show my kids some Swedish TV show, I can't do it because for whatever reason this tax-funded, tax-sponsored TV station will not show their movies to outside the country. Maybe because nobody's paying Swedish taxes if they're outside the country, I don't know. So I can now buy a subscription to one of these services with a Sweden endpoint, right? And now it will look like I am browsing from within Sweden, and then I get to see the movies. And it's also pretty good because then they cannot identify like that service, the end service that I'm using, not the anonymizing VPN. They can't tell who it is that's using it, and so this TV channel can't come after me saying, "Oh, you have to pay fees because you browsed it from outside the country." Not that they would, but generally, sort of a handy service that way. And certainly, if you're doing any BitTorrent downloading, is a very good idea because that can get expensive, is my understanding. So those are pretty good, but it's not, it's not really hardcore protection here, because if whoever's trying to see what you're doing, if they have access to your network traffic, even if it's encrypted, they can see that you have a VPN tunnel, right? Or there's encrypted traffic, lots of encrypted traffic going from your machine over to that other encrypted tunnel. And at least if we're talking about serious operators here, right? Now it's law enforcement or it's some very well-funded criminals. Then they might be able to now see what traffic you have, and they can see what traffic is coming out from this VPN service provider, right? If you infect a device in your home, like your Netgear router, whatever, and then you infect a Cisco router on the other end where this VPN service is running or somewhere nearby, now you can tell, whenever he sends a packet over here, a few hundred milliseconds later, a packet goes out from over there with a similar size. So you can kind of correlate the traffic between me and this other VPN site, and now they can tell that, he's the guy viewing all those Pippi Longstocking movies, right? And so that gets pretty expensive, and I don't think that Swedish Television would go to that extent, but in general, it's not great if you're doing something that's dangerous Like if you're running a political party that's forbidden in your country, let's say. So this is not good because it can be subverted by traffic correlation attacks. And it's also not so good because this VPN service, it's very clear who is running the VPN service. So if they are doing this politically subversive activity, they might be blocked. So their IP addresses might be blocked in the country or whatnot. And so the VPN service provider is potentially liable. Right, yes?
Do the traffic correlation attacks include the placing software on like both ends routers and sniffing packets that way, or is that something separate?
Yeah, you would. It might be sufficient to sniff at the subversive website and at your link, and now you can see like two packets back to back of these sizes went out, and then two packets back to back of these slightly smaller sizes came in. And now, if you keep doing that over some significant amount of time, now you have reasonable evidence that this was the person doing buying the drugs on this website. Let's say. It would be better to do it at the VPN service provider because there you have like tighter control, but it might be harder to do it there. At least if you're law enforcement, it'd be much easier to get a subpoena to look at traffic at a certain website rather than generic VPN service provider. Okay, so these are pretty good, and something I think is enough for most sort of typical uses. If you are more concerned than that, if you're doing things that are properly dangerous, the next step up is the onion router, Tor. And I think we can find a little diagram for that. Let's see. Okay, this is good. Right. So here the general idea is Alice wants to talk to Bob, Bob being a website, let's say, and this is a normal website, nothing special, but Alice doesn't want anyone to know that she's visiting this website. So she might be in a country where this website is illegal, let's say. Say I'm in China and I want to use Google. Google's illegal in China, and so I would use Tor. And the general idea then is I send a request to one of many Tor routers. And inside, actually, maybe we need a little drawing after all. I'll copy this. I'll hide it down here. Let's see. Oh, here it is. Good. Okay, so we have Alice and Bob. And Alice would say, there's a secret request, R, and here's the reason why it's called an onion router. Let's make this a 3-layer onion. So there's a secret request. This is the plain text request that's meant to go to Bob, like HTTP get your website, your web page. But it's wrapped in another layer of headers that is basically just a TCP connection, let's say, and it's encrypted. That says, here, let's see, go to this machine. In fact, in this example, we should have a few more. Okay, so in the first layer of this, Alice is connecting to this machine. She's picked this machine at random, so let's call this A. The traffic will go to A. And then Alice has picked So this is an encrypted bit of traffic here, like the whole packet is encrypted, and inside of it, she's put directions to send. Actually, let's say she sends all of this to A. That's better. And then inside of it is directions to forward it to machine G. And inside of that is another one that says to send it to machine L, and finally to send it to B. Bob. Right. So Alice will send this onion packet encrypted to A. A decrypts it and sees the contents. This is sort of an encryption boundary here. So A sees the contents of it, and the contents basically says, oh, forward this to G. And then there's this encrypted stuff that's supposed to be forwarded. This is encrypted with a different key now. This is a key for G, which is this one in this example. And then G will forward it to L. Let's see, G decrypts the message, sees that it's supposed to be going to L, which is this machine here. L decrypts its message, it sees it's supposed to send it on to Bob. And so now it's saying sends the plain text, if you want, message finally to Bob. Yeah.
How is the path determined ahead of time yet obscured from each host?
Yeah, so it's actually let's see now. So Alice will pick a random sequence of hosts. So she will say like yeah, there's a set of routers that she knows about, and she just says, okay, I'm gonna have the last hop as L, right, and then encrypt that, and pick another one, encrypt it for the next one before that, and so on. Right, now I don't remember the return path.
I have another question.
Yeah.
So the L represents the last router before the destination host.
Yeah. So this would be called the egress router. Here, let me put some labels on them. So I just picked some random IDs here, right? This was just to give one example, but here the plan was we had it like this. Right? And now Bob would have to, so yeah, unfortunately, I don't recall the plan for the return. It would be very bad if Bob knew who Alice is. So that's not what's going on. I'll have to look that up and post it later. Yeah.
Yeah, my question was just about that. I was wondering if maybe Alice had to calculate the return path as well, and then send that to Bob.
Yeah, I don't think that's the case. Yeah, maybe we should look it up. Yeah.
And then my last question is in the last router, or that goes to Bob and then back to Bob, is unencrypted, or at least it indicates it's unencrypted. And I was just also wondering what that means.
Yeah, this actually looks a little funny. I'm not sure that this diagram is right. That's what you get for grabbing random diagrams off the web. Bob, of course, should be corresponding with L. Like Bob is a normal website. The traffic wouldn't go to some other Tor node. It would go back to L, and then so one situation that I've seen is that Alice sets up a permanent path for a little while, and that's how the response comes back. But I'm drawing a blank on how that actually worked. Let me see if we can refresh my memory. All right. No, I will have to look that up later. So so anyway, the beauty here of Tor is that you're sending traffic to A, and A can see it's coming from you, but it can't actually tell where the traffic is going. And now G can see, oh, the traffic came from A, but it doesn't really know that it came from Alice. Like, there's no indication that it came from Alice. And then so on. So now if you go enough times and you mix with other traffic, the general idea here is you want to have lots of users that are all using these Tor routers, sending traffic through them. And now it starts getting harder to distinguish between packets from one user versus packets from another user. You go through several of those steps, you have a large mixing set, and now everyone is more or less anonymous. Bob can tell that it's talking to this machine, but it can't tell who the originator was. And we'll have to follow up on how L here sends the return traffic back to Alice. So this is nice because now we have basically no way to do the correlation attack. Really hard. But the end hosts are still, yeah.
So I think when it gets to Bob, it creates a chain of assigned addresses assigned to the public key of the current node, and it's a stack. So the last node decrypts the last address. So.
Okay, yeah, this makes sense. So one good way that we could do this is we send our packets, and now A remembers that for this flow, the request came from Alice. So when I get a packet in the reverse direction for some flow ID, then we can encrypt it with the key that we have between us and Alice, and we're okay. So same thing for G. G would take incoming packets from L and add on a layer to the router and give it to A, and so on. So it sort of adds on layers all the way, and now these intermediate routers, they don't know that it came from Bob anymore, and that would be fine. And this relies on having a sort of ongoing session or a session ID, and I guess that's in place somewhere. Right, so that's overall, that's pretty good. Unfortunately, it was revealed, I think a couple of years ago, that I believe it was the NSA, they were able to capture most of the traffic from almost all the Onion routers. Right? So basically, if you sniff on most of the big links of the internet, like you attach things to undersea cables or you bribe some operators and so on, you can get access to those very high bandwidth kind of core cables, and then you get most of the traffic. So in this case, we have this beautiful grid diagram, right, of all these machines, but in reality, they're all over the world. Right? So this might be here, and then we're in Sweden, and then we're here again, and then we go over to some other place. So we're crossing all these global links several times to get between these routers. So we don't actually have to instrument links right next to each router. As long as we have several of the core links, we're able to capture most of their traffic. So I think that was the principle. Of course, they wanted to keep that secret, but it came out at some point. And so if you have most of the traffic from most of the routers, then you can do successfully a correlation attack. And now you will know for every entry ingress point here to the network, which is the egress. So you know who's talking to who. And then you've lost the whole point of the Onion router. Of course, this only works if you're a truly major operator in this case, but you could easily imagine criminal syndicates, this sort of thing, also relying on the Onion router and being taken down basically by a correlation attack. It's sort of an interesting idea. You know, it's always an arms race between the attackers and the defenders. But I also like this idea that the onion router was initially was created by the Department of Defense. It was funded by the Department of Defense. And at some point it kind of turns around and becomes a vulnerability for a criminal league because they're relying on it. It's a fun game. In any case, you're still potentially liable for operating one of these nodes. Bad things are happening, and you're one of those machines who are supporting those bad things happening by participating in the onion network. That can be a risk. And of course, you could try to block every onion router. If you have a known onion router, say a router that publishes its existence, says, I want to participate in this network, a country that doesn't like that can just block that IP address using their national firewall rules. So it can potentially be filtered out. You can run it in a sort of a darknet mode as well. If you don't let anyone know that you are running an onion router, then you and your friends can onion between yourselves, and it's going to be harder to filter your machines because nobody knows that this is that you're an onion router. So now your friend's traffic from China can look like anyone's traffic, and it's actually going through another friend in Europe and then through you, and now it's just a request to Google, and that looks perfectly legit from a Chinese perspective. Okay, next up, we can take it a little further than that. The problem here is if you're publishing content that isn't generally desirable, then just by the fact that you are publishing it, you can probably be tracked down. It's really hard to serve content without having your location be known, right? Because you're always you're sending packets out, and it has that content that people don't like you to have. I think the onion router helps some. You can run an anonymous website. There's something called onion services too, where you don't even have an IP address. An onion service just has a sort of an onion ID that you can route to within the network, and it's more privacy protected. Well, one level up from that is called Freenet, which is kind of charming. In Freenet, Freenet is basically a distributed least recent use (LRU) cache. If you want, you can take a piece of content and you can add it to the Freenet. So it supports two functions: put with some key content, and then you can get with some key. The key is a number between 0 and 1. If you want to join the network, you pick a number between 0 and 1 and you say, this is me. And the general rule is, when you put something, you try to put the content at the closest possible member. So someone has a number that's, I'm 0.5 and the key is 0.51. Well, probably I should be in charge of it. Okay, so now we have a whole bunch of nodes. They pick a random number between 0 and 1. They connect to some neighbors. They don't know who all the neighbors are in Freenet, because Freenet is very shady. So they just know some of their friends, but their friends know some other ones. And you try to remember all of your local friends' IDs. So if you want to get a key, you send a query toward the friend with the most similar ID. So we're sending out. In fact, I had a nice picture. Let me see. I think I lost it. Okay, this will work. Okay, so here I'm sending a request. The data is stored at some node that has a key similar to the data's key, but I don't know where that is at all. I don't even know about D's existence here, the node D. But I have a friend B who has a key that is more similar than mine to this data. So I will send my request to B, and B will do the same thing, kind of send out its requests. And then over time, the query will sort of get closer and closer to the node that holds this data. And we don't really know when that happens, but at some point, I say a node along the way says, I have the data, so it just returns the data. Or if it doesn't have the data, it forwards the query. But from an outsider's perspective, there's no way to tell whether the node forwarded the query or returned some data. So you could be the forwarder, or you could be the holder of the data, and no one's the wiser. Key to the network actually working is that every query has a unique identifier, so you don't kind of forward queries that you already saw. It's more of a broadcast. Like when you do a query, I think you more or less broadcast it out. But when you store something, you have to get it to the right spot, the one that's closest to the key of the ID. So what's really nice about Freenet is it's actually storing the data at some random location, and no one can tell really where it's stored. Maybe one drawback of Freenet is, advantage, data is stored. And potentially more than one node. But the disadvantage is that now anyone can insert stuff into the network. Of course, this means, and the network is then responsible for hosting it. So this means that there's no sort of disincentive to publishing more and more stuff in the network. Data will grow unboundedly, and of course we can't handle that. So we end up with expiring data relatively quickly. Data that isn't accessed frequently expires. So if you have some deep secrets that need to be stored somewhere, and they're important secrets, you may not be able to put them on Freenet because they won't be there when you need them later on. But if you're publishing some political treatise that is sort of too hot for anyone to want to actually publish, like no one's going to run a website that has this piece of text on it, then Freenet is the right place, because you can't really remove anything from Freenet. There isn't a delete function, and the data, if you take down one node, another node will be storing the data, and it's sort of it's quite resilient to that. The data is also, there's some details there, the data is also stored on multiple nodes, and yeah, it's hard to erase things, other than by just flooding it with content. So I think that's the main disadvantage, probably. It's vulnerable to a denial of service attack where you just store lots of stuff, and there isn't anyone that can say, oh, you're not allowed to store stuff on the network. That's the whole point. Everyone's supposed to be able to use the network for whatever they want. So probably if it was to be a sort of a big mover in the political arena, then another big mover would come in and quickly fill it with irrelevant stuff, and then it doesn't work anymore. Freenet also has a sort of darknet mode where you can, where you don't say I'm a Freenet node, you don't publish your existence to anyone, you don't try connecting to random people, you only connect to known users, and in that case it's very safe, very hard to detect. Okay, so yeah, I think the problem with all of these things is it tends to mostly attract nefarious users. I think there is a really legitimate argument for these services. Like in some places, I mean, it's kind of ridiculous, at least in China, in my opinion, that you can't use Google. Like that is something that probably is worth fighting for, the ability to do that. On the other hand, it's probably not so sensible that anyone should be able to publish whatever they want. Some documents may cause more harm than it's worth, in a sense. I guess the most, what's it called, the archetypical example of that is child pornography, where there's really no positive aspect to it, and it's sort of the most popular use of Freenet, at least for a while, because it's so hard to track anyone down. It's so easy to store things. It was a good use, like a popular use for Freenet, and so that makes it not something you want to work on. So difficult balance there. Okay, so we're supposed to talk about security as well. I think we'll spend some time in the next lecture as well, but let's get a start on it. So the most important, security has many different aspects to it, and if you look at our curriculum, there's lots of security classes, and most of it has to do with various sort of vulnerabilities due to bugs in programs. And those are a separate concern that we're not going to talk about in this class, but I'm sure you're familiar with buffer overflow and that sort of thing. There's lots of other potential security flaws, both due to program errors and due to processor or sort of hardware errors. Lots of interesting work there. But one that's very specific to networking is denial of service attacks. So generally, denial of service is this idea that you insert some traffic into the network so that either a particular client or a particular server don't get to do their normal job. So one thing you might do, say a server is, there's some various things you can ask a web server to do, and one of the things you can ask it to do is to compute something expensive. So now it's a normal web server, and usually they just serve a normal website, but they also have this thing where it can kind of factor some integer. You know, an example little piece of code for factoring some integers, very cool. So now, if someone discovers that little cool service, they might issue lots of requests to factor integers, and as you know, that takes a long time. So if I just issue lots and lots of such requests, the web server will be too busy factoring integers to do any of its normal work. And that's a typical denial of service attack. So basically, resource depletion to deny others service. Right, so, okay, maybe normally websites wouldn't publish such a service, like factoring integer service, but there's lots of other things they do that are sort of similar. So one thing that you may have seen is, well, you have seen, of course, is DNS requests. You can issue a small DNS request, and you can get a large response. So now, if I want to bring down a website, I know I only have a 10 megabit connection, I can choose to try to send 10 megabits of data to this website, just any packets. And the packets will make it there. There are no rules anywhere preventing me from sending 10 megabits of UDP packets to this website. But they probably have a connection that's faster than 10 megabits, so they'll be annoyed, but it's not going to be the end of the world. A good way to improve my situation, let's see, okay, tag 1, send lots of UDP packets. A better way might be to send lots of DNS queries. So now I have 10 megabits that I can spend, and I issue these maybe 40-byte long DNS queries. Not to the host, not to the end host, because they're not going to answer any DNS queries. And anyway, that's only 10 megabits. Instead, I send it to other DNS servers all over the place. And now they will respond with 500 byte long requests. Actually, it was 40, make it 400 bytes long request. Response. Of course, if they respond to me, now my website, my connection is down. That's terrible, getting all these UDP responses. So I put the website's IP address as the source. Right? So I send a query on their behalf. Right? So now they're going to get 10 megabits worth of responses, but times 10 because the response was 10 times bigger. So now they get 100 megabits worth of DNS responses coming in with target as the source, IP source. This is called magnification. So this is relatively common. And another beautiful thing about a magnification attack is or at least this magnification attack is they can't even tell that it was me, right? So initially I was sending from my IP address 10 megabits worth of traffic, using up 10 megabits of their link. Now it's thousands of DNS servers sending together 100 megabits of traffic, and they don't know why. So that's nice. But maybe you could still tell that it's DNS queries, right? And so you could, or DNS responses. So you could, on the receiver side, you can try to protect against that. Once you've detected sort of the nature of the attack, suddenly at some point there's 100 megabit of stuff coming in, and you don't know why initially, and then you start looking at TCP dump, and you see, oh, it's all DNS responses. What's up with that? And then you put in a filter at your ISP somewhere upstream that says, just throw away all DNS responses, right? All DNS responses except from these 3 machines, which are the ones I'm going to be talking to. For the rest, just throw them out. And now the attack is gone, right? It affects your ISP, but they have much more than 100 megabit of connection anyway. The attack isn't that effective anymore, so whoever's launching the attack are going to stop doing it pretty soon. So that's a good countermeasure. So next up, we want to start thinking about distributed denial of service attacks, and we'll do that next time. All right, and please post if you have ideas for other things you'd like to hear about in the next lecture, which is the last lecture before the sort of semester wrap up. Please post them on that Piazza post. All right, thanks. I'll see you on Wednesday.